All right, folks, it's afternoon for me. It's something for you. So today what we're going to do is look at a few more ideas about the thermal effects of materials. And then we're going to close this section of the course on thermodynamics, looking at using ideal gases as heat engines, something that takes heat and turns it into mechanical work that we might use. All right. So to start with, though, we're going to look at how an ideal gas absorbs heat. Right. Now what I want you to do is remember that we had looked at how solids and liquids absorb heat. Right? And that's this specific heat business, right? That the amount of heat that is absorbed by the material to change its temperature some delta T is going to be the mass of the material times this constant, the specific heat of the material, times delta T. All right? So it's a linear relationship between the heat and the temperature change. Right? This is for solids and liquids. And each solid and liquid, of course, has its own specific heat. And the M is how much of that material do you have. Now, one thing to notice is that we don't have any conditions here for how this material is being heated. What is the pressure, or if the volume changes, or whatever. And that's because with solids and liquids, volume changes, effects due to pressure are almost insignificant for relatively moderate changes in temperature. So this works fairly well across almost any kind of range, again, for a solid or a liquid. And one final thing, of course, we could change this to the molar specific heat. And then instead of the actual mass in kilograms, we would have the number of moles here. All right. The difference now is, in an ideal gas, we have to worry about how do we get there? How do we get from one temperature to another? So let me start off then with a diagram. All right, here is one of those PV diagrams. Remember, we've got pressure on this axis, volume on this axis. What I'm going to do is I'm going to plot some isotherms, right? So I'm going to plot some lines that show me where constant temperature will be along in this region of PV space. So here is one, and let's call that temperature 1. Here is another one, and let's call that temperature 2. All right? And remember, because PV equals nRT, right, that these constant temperature isothermal lines are inverse functions, right? That the pressure goes inverse to the volume for a constant temperature. All right? We'll have P equals nRT divided by V. Right? So if we have a constant temperature, the pressure is varying inversely with volume. Okay, so we have a couple of different processes that we know now for making changes between being at one spot and another on this PV diagram. Our thermodynamic states are one spot: a pressure, a volume, a temperature. We can go to another spot using a thermodynamic process. And remember, we have 4 of them. All right. One of the processes is an isothermal process. Well, if we're going to increase the temperature of something, that throws isothermal processes out the window because they don't change temperature. All right, can't use that. What about this adiabatic process that we learned about, right? That one's gone because there's no change in heat. There's no heat input to the system. Ooh. And we're heating this. So that's not the process that we want. So the only other two are the isochoric process, a constant volume process, or an isobaric process, constant pressure. So we have this possibility. We could start off at this initial spot, some initial pressure, some initial volume, and some initial temperature, which is T1, and we could do an isochoric process, constant volume, right? It would take us up here to some final spot at our new temperature, right? If we start here and we do a constant volume process, absorbing heat during this constant volume process, to get to the second temperature, then it has to follow that line because it's a constant volume line. So there's the new spot that we would end up at, the new pressure for that new temperature at this specific volume. Now the other one, so this one is the isochoric or constant volume process. Here is the isobaric process, right? That would take us from our initial to our final state. Again, we know that if we start here, we supply heat, we increase the temperature, doing a process that is constant pressure process, right? Then here is where the new volume value will be at this new temperature. All right? So diagrammatically, this is what's happening for us. All right? Now, it turns out, not surprisingly, that if we do these things and we try to look at them like we did with solids and liquids, we get the same kind of effect happening. A linear relationship between the heat that we have to supply and the temperature change, right? And so we get Q equals, right, the NCV delta T for a constant volume process, constant volume. And Q equals N C sub P delta T for a constant pressure process, right? Just like we had earlier, right? We had written Q equals MC delta T, the amount of material, some constant that we call specific heat of the material, and the temperature change. So analogous to what happened with solids and liquids. Here though, we have two different values for the specific heat. This one is the specific heat for constant volume. This one is the specific heat for constant pressure. Because we're going to find out that those have two different values when we look at ideal gases. Again, here's the key. When we looked at a solid or a liquid, right, as we supply heat to this, we don't really care whether there's a lot of pressure on the solid or not, right? We don't care about whether or not the volume is changing. Because for solids and liquids, for these kinds of temperature changes, those values don't change very much. All right? But think of heating up a gas. It expands, right? So the volume, volume not constant unless I confine it to a particular volume. Then I will have a constant volume process, but you know what happens? You create a bomb, right? The pressure skyrockets. So here is that constant pressure process, the constant volume process, the two equations that tell you what happens with them. So now, let's see if for an ideal gas, we can figure out what this value of CV or CP should be. What we're going to find out is, for true ideal gases, that there's specific fixed numbers for these, as compared to the solids and liquids, where for each material it's different. So let's take a look at this. Let's see, let's pick the one that we're going to do first. The one we'll do first is the simpler one. It'll be the constant volume process. So we're going to concentrate on this one first. All right? So what I'll do is I'll give myself a little bit of space here and try to keep my diagram there still in the picture. All right? So here we've got, what we're going to do now is use the first law of thermodynamics. All right? And the first law of thermodynamics is going to tell us that our change in the internal energy has to equal the heat that comes in and the work that's done, right? And that we wrote as delta U equals Q plus W. The heat that you put into the material, the work that you do to the material, gives you how the energy, the thermal energy internal to the system increases. All right? Now, remember, for an ideal gas, what's the internal energy look like? It's one of the first things that we mentioned with an ideal gas, that the internal energy, this delta U, or the change in the internal energy, is always going to be 3/2 Boltzmann constant times delta T. That's true no matter what flavor of ideal gas you have, as long as you can model it as an ideal gas. All right, as long as you can model it as an ideal gas. All right, so that equals, well, let's use now the equation that we wrote down for the heat that will be absorbed, the linear relationship for this ideal gas in a constant volume process. Okay, well that was the specific heat deal, right? So that's N, C sub V for specific heat at constant volume, right? Times delta T, plus the work done to the gas, right? Maybe you see where this is going. Look at this curve right here. Hopefully you can still see it. I think you can, right? This curve here represents the process that we're doing. And we recognize there's no volume change. There is no area under this curve. When I do this with a constant volume, no work can be done to the gas. No work can be done by the gas. And so, this work for this process is 0. Wow. Straight away, I see that I've got my answer as to what is the specific heat for a constant volume process for an ideal gas. Look, this should have an N also, right? This is the average energy change per particle, and we have to put in the number of particles right there. So it's 3/2 K delta T N. This is NCV delta T. Now I can cancel the N's out, right? And the delta T's go away. And I see that the specific heat for constant volume is 3/2 times the Boltzmann constant. Any ideal gas, no matter which one you want to look at, has this for its specific heat.